What are the exoplanets at the edge of our galaxy truly hiding? Dear traveler, greetings. Today we embark on a journey beyond our solar system to invisible worlds to the naked eye, but revealed by the patience of telescopes. Some are burning gas giants, orbiting so close to their star that a day lasts only a few hours. Others are icy planets, lost in eternal shadow, where storms of incredible violence rage. And there are those, even more mysterious, worlds similar to Earth, covered with oceans, perhaps forests, perhaps life. But before setting off on a new adventure, don't forget to like the video and subscribe to the channel to not miss anything. Thank you and have a nice trip. Leaving Earth, we leave behind all daily concerns to dive into the vastness of the cosmos. Even before catching a glimpse of the light from Proxima Centauri, the star closest to ours, one must understand why this star has fascinated for generations. It is a red dwarf, smaller and colder than our Sun, classified in the M type, characterized by a lower surface temperature. Proxima Centauri peaks at about 3,000 degrees Celsius, compared to 5,500 for our star. This lower temperature gives it a distinctive reddish hue. More modest in size, Proxima Centauri shines much less than the Sun, which considerably brings its habitable zone closer to the star. It is also subject to activity episodes, such as eruptions and light variations, which can influence the formation and atmospheric stability of its planets. In this context, the confirmed discovery of Proxima Centauri d arouses great interest. Long suspected, its existence was made official thanks to improved detection instruments. Confirming an exoplanet is a long and methodical process. Researchers use the radial velocity method, or wobble, which involves measuring with a high-precision spectrograph the tiny oscillations of the star caused by the gravity of its planets. In the case of Proxima Centauri d, a signal of about 0.4 meters per second was detected. This figure, minuscule on an astronomical scale, nevertheless reveals the presence of an orbiting body. After repeated measurements and the elimination of other possible causes, this planet moved from the status of hypothesis to that of confirmed discovery. Once its presence was established, scientists focused on its mass and nature. Estimated to be about 0.26 times that of Earth, it falls into the category of sub-Earth planets, less massive than ours, and likely to present different geological or atmospheric characteristics. Its exact composition remains to be determined, which will require more advanced observations with future space instruments. Proxima Centauri d completes an orbit around its star in just 5.1 Earth days, receiving about 190% of the sunlight that Earth receives from the Sun. Its proximity could place it in tidal lock, with one side always lit and the other in perpetual night. In this case, heat distribution and atmospheric circulation would play a key role. Some simulations suggest that a thick atmosphere could maintain a temperate zone, but many unknowns remain: chemical composition, protective magnetic field, volcanic activity, sharps. Its proximity and conformation make it a priority target for advanced instruments like the NARPS infrared spectrograph and the James Webb Space Telescope. NARPS, from Earth, tracks radial velocity variations and searches for possible chemical signatures. The James Webb, with its sensitivity in the mid-infrared, can measure the heat emitted by the planet, particularly during its transit behind the star, allowing inference of its temperature and some surface or atmospheric properties. The upcoming data could reveal if Proxima Centauri d has an atmosphere, its actual temperature, and the possible presence of molecules like oxygen or water vapor. Even if it is not an extraterrestrial paradise, studying it allows testing and refining models of planet formation and evolution around red dwarfs. Proxima Centauri also has other planets, like Proxima Centauri b, located closer to the habitable zone. The multiplicity of these worlds reinforces the idea that complex planetary systems are common in our galaxy. Proxima Centauri d, although modest, illustrates the growing sensitivity of our instruments, capable of detecting planets lighter than Earth. Its strong irradiation raises questions about its climatic conditions. An orbit so close subjects it to stellar winds, which could erode a potential atmosphere unless a strong magnetic field protects it. For now, there is no definitive proof of an atmosphere's presence, and the planet could be inhospitable to life as we know it. The coming years will be crucial to refine measurements and attempt direct observations. Proxima Centauri d also offers a unique opportunity to test theories on planetary formation around red dwarfs and the resilience of atmospheres to extreme conditions. Its proximity facilitates data collection with unmatched precision, making it a true astronomical laboratory. Beyond science, it fuels the collective imagination. One day, perhaps, fast probes will reach Proxima Centauri, the first step of an interstellar odyssey. Until then, its meticulous study continues, mobilizing spectrographs, climate models, and magnetic analyses. Each discipline contributes new elements, closely followed by the scientific community and exploration enthusiasts. Barnard, a discrete star located nearly 6 light-years from our solar system, is among the astronomers' favored targets to explore distant worlds. For those unaware, it is a red dwarf, a star of low luminosity and small size compared to our Sun. Despite its reduced brightness, it has captivated researchers' attention for decades. Its apparent motion across the celestial sphere, considered abnormally fast since the early 20th century, sparked inquiries about the potential presence of orbital companions. It took many years to confirm the existence of several planets around it. Today, we know that Barnard hosts a collection of small rocky bodies, a true planetary mini-flotilla that intrigues as much as it amazes. Let's dive into the heart of Barnard and its worlds, with a particular focus on the recent discovery of 3 additional planets, Barnard C, D, and E. The letters that designate them indicate the order of their discovery, not their distance from the star. Their identification required patient work and multiple verifications. It was the radial velocity method that allowed their detection. It measures the tiny oscillations of a star under the gravitational effect of its planets. The star, engaged in a subtle dance around a common barycenter, betrays these movements through tiny variations in its light's wavelength. This data reveals the mass and orbital period of each planet. The estimated masses of the 3 newcomers range between 0.19 and 0.34 times that of Earth. In other words, these are sub-Earth worlds, lighter than our planet and probably rocky. Their low mass excludes them from the super-Earth category and further distinguishes them from giant planets. Their complete revolution around Barnard lasts between 4 and 7 days, a frenetic pace due to their extreme proximity to the star. These tight orbits result in intense irradiation, excluding any presence of liquid water on the surface according to our current habitability criteria. The probable temperatures far exceed the limits compatible with known organic chemistry. This compact configuration, however, attracts great interest. It allows testing of very high-precision instruments on a clear and measurable multiplanetary system. The combined oscillations of radial velocities serve to refine models and perfect detection methods, paving the way for the future identification of even smaller worlds. Their sub-Earth nature also raises questions. How do such assemblies form? Around a red dwarf like Barnard, the initial protoplanetary disk might favor the emergence of many small bodies rather than a few large planets. In this specific case, the worlds seem to have remained close to their star while limiting their growth. The system also exhibits weak resonances. The orbital periods approach simple ratios without reaching them exactly. The study of these configurations sheds light on the history of planetary migration and past perturbations that have shaped their current arrangement. This miniature laboratory perfectly illustrates planetary migration. Here, the planets likely slid slowly into their current positions, thanks to the longevity of the gas and dust disk, preserved by Barnard's low luminosity. Their arrangement tells part of their history and the forces that have shaped them. For a long time, attention was focused on Barnard B, a more massive world located further from the star. The conformation of C, D, and E opened a new chapter. These planets, although scorching, could one day reveal rare or exotic atmospheric clues. They also constitute ideal targets for the most advanced spectrographs, capable of detecting tiny radial velocity variations, comparable to a very slow human step. This precision is crucial for detecting small exoplanets, particularly around red dwarfs. Barnard's rocky mini-fleet also challenges our perception of planetary architectures. Far from our varied solar model, it shows a compact group of similar worlds, perhaps much more common in the galaxy. The intense irradiation they undergo also allows the study of photoevaporation, the process by which an atmosphere escapes under the effect of radiation. The energetic emissions of a red dwarf can cause notable atmospheric losses, observable with sensitive instruments. Even without water on the surface, these planets could harbor, deep down, unexpected reserves if internal mechanisms maintain sufficient heat and pressure. At only 6 light-years away, Barnard is easily accessible for repeated observations. Its relative brightness for a red dwarf makes spectroscopic surveys easier. Numerous publications already highlight its importance, a discrete but planet-rich system that pushes astronomers to more systematically target red dwarfs in their quest. The gravitational interactions between C, D, and E, although weak in the short term, shape their evolution over the long term. Their study nurtures the bouquet-shaped planetary formation models around small stars. Geologically, only the mass is known. Their density and composition remain to be determined due to the lack of observable transits. Radial velocity thus remains our main tool, while waiting for more effective methods capable of detecting the light reflected by their atmospheres. The estimated temperatures exceed several hundred degrees, making any life as we know it unlikely. However, caution is required. Some nearby planets exhibit unexpected rotations or thermal distributions, which could alter the surface conditions. Studying these inhospitable worlds is essential. Barnard offers an ideal testing ground for refining technology before applying it to more temperate targets. At the heart of our cosmic odyssey, let's stop between 10 and 40 light-years from our solar system. In this relatively nearby zone on a galactic scale are stars with discrete charm, M dwarf stars. Less luminous and less massive than our Sun, they are prime targets in the search for extrasolar planets. Their faint glow facilitates the detection of orbiting worlds, and their moderate temperature can host habitable zones at close distances. Imagine a vast ocean of darkness where a modest reddish hearth gleams. These M dwarfs, sometimes referred to as quiet when they remain calm, release few violent eruptions likely to disrupt their nearby planets. It is in this environment that we will discover a fascinating array of exoplanetary systems, with the star being L9859F, located about 35 light-years away, as well as a string of mini-Neptunes detected around other M dwarfs within a similar radius. The M dwarfs are one of the most widespread stellar classes in our galaxy and dominate among nearby stars. Their surface reaches only a few thousand degrees Celsius, much less than the 5,500 degrees of our Sun. Their small size reduces their brightness, so much that their habitable zone is much closer than it is for Earth. In these systems, it takes only a few days or tens of days of orbit to find oneself in a region where liquid water could exist. This modest size offers a major advantage. The variations in light or gravity caused by a planet are easier to observe. That's how L98-59F was detected. Its host star is located 35 light-years away. The letter F indicates that it is the 6th planet detected in this system. With a radius close to that of Earth, it falls into the category of rocky planets of comparable size. Its discovery is based on the radial velocity method, which measures the tiny variations in the star's speed under the gravitational influence of the planet. Like a dancer influenced by a lighter partner, the star wobbles imperceptibly, producing a slight shift in its light. This extremely precise technique is even more valuable because the planet does not transit in front of its star. L. 98-59F is located in a temperate zone where the heat received would, in theory, allow for the presence of liquid water. However, the actual temperature depends on still unknown parameters, such as the composition and density of its atmosphere. If the atmosphere is limited, the planet could maintain moderate conditions. Specialized instruments, particularly in the infrared, could reveal the presence of water vapor, carbon dioxide, or other gases indicative of geological or biological phenomena. Let's continue with the string of ultra-close ones, G192-15, B and C, G261-6b, and G268-110b. These are mini-Neptunes, larger than Earth, but smaller than Neptune, with orbits of less than 15 days. Their proximity to the star often leads to extreme temperatures, beyond habitable conditions. But their interest goes beyond the search for life. They shed light on the formation, migration, and evolution of planets. Their interiors, rich in light gases or ice, raise questions about their origin and history. These worlds also offer unique opportunities for near-infrared transmission spectroscopy. When a planet passes in front of its M dwarf, part of the light passes through its atmosphere. By breaking down this light, we can identify molecules like water, methane, or carbon dioxide. The reduced contrast between an M dwarf and its planet makes it easier to detect this faint signal. The close mini-Neptunes are thus ideal laboratories to test the sensitivity of our instruments. By measuring both the size and mass of these planets, astronomers can estimate their density and therefore their composition. A high density suggests a rocky core, while a low density implies an envelope rich in gas or ice. Mini-Neptunes, with their gaseous mantles and crushing atmospheric pressure, are very different from Earth, but each of them enhances our understanding of planetary architectures. The stellar activity of M dwarfs plays a decisive role. The calmer ones favor atmospheric stability of their planets, offering a better environment to maintain water and a moderate climate. Even if the presence of liquid water remains hypothetical, the proximity of these systems makes them ideal targets for ground and space telescopes. Technological advances and improved algorithms now allow us to detect tiny signals, revealing planets much smaller than the giants once favored. The observation of M dwarfs, which mostly emit in the red, makes the slight brightness variations related to a transit more perceptible. Detecting the chemical signature of an atmosphere over multiple transits could reveal clues about the climate, geology, or even traces of biological activity. If one day we develop probes capable of traveling several tens of light years, these worlds would be among the first to be explored. Between 10 and 40 light years away, the ring of quiet M dwarfs concentrates systems of exceptional scientific interest. L9859F, close to Earth's radius and in a temperate zone, excites curiosity. Mini-Neptunes, larger and easier to observe in the infrared, offer a testing ground to refine our techniques. Their diversity challenges our models and invites new hypotheses on planetary formation and evolution. During this imaginary journey, we enter a region located between 40 and 100 light-years from our Sun. It hosts numerous M and K-type stars, less luminous and cooler than our star, but which ignite a keen interest among astronomers. Although two of the targets studied are slightly beyond this distance, their observation enriches our understanding of what is called the fast-paced M and K squadron, a group of stars that are galactically close, around which planets orbit in a time very short compared to our Earth year. To locate these stars, remember that the astronomical classification follows the sequence O, B, A, F, G, K, and M, determined by surface temperature and other spectroscopic criteria. Our Sun is of type G. K stars, cooler, have a temperature between 4,000 and 5,000 degrees Celsius, are less massive and less luminous, which facilitates the study of small planets. M stars are even cooler between 2,800 and 3,700 degrees, less massive and emitting a more red light, hence their nickname, red dwarfs. A super-Earth is a planet whose mass is between 1 and 10 times that of Earth, but well below that of giants like Neptune or Jupiter. Generally rocky, it could possess a denser atmosphere, a larger surface, or a more intense magnetic field. These characteristics fuel the hope of one day finding habitable worlds or ones rich in water and complex molecules. To determine the density of a super-Earth, astronomers combine two methods: radial velocity, which measures the tiny wobbles of the star caused by the planet's attraction, and transit photometry, which observes the drop in brightness when the planet passes in front of the star. These data allow for deducing mass, radius, and density. Added to this is the technique of transit timing variations, or TTV, which measures the tiny shifts in transit times due to the gravitational influence of other bodies. Now let's leave the 40 light-year zone to reach at 124 light-years away, the star GJ 2126. This red dwarf, with a surface temperature of about 3,000 degrees, is invisible to the naked eye, but draws attention thanks to its planet GJ 2126b. This super-Earth orbits in only 5 to 6 Earth days, several dozen times a year compared to our calendar. Too close to its star to be temperate, it likely experiences several hundred degrees on its surface. Inhospitable for life as we know it, it remains valuable for density measurements by TTV, as its short period allows for multiplying observations over a short duration, perhaps revealing the presence of other bodies in the system. At 152 light-years is Ross 176, a star of type M or K according to catalogs, and its planet Ross 176b. Again, we are dealing with a super-Earth with a very short orbit, with extreme surface temperatures. Although not conducive to life, it offers an ideal testing ground for TTV techniques, especially since systems of this type often host multiple planets interacting gravitationally. The tiny shifts in transit times, sometimes only a few seconds, become a treasure trove of information on mass, internal structure, or orbital organization. These planets also raise the question of their origin. Did they form near their star, or did they migrate from more distant orbits? The study of GJ 2126b and Ross 176b allows testing these scenarios and refining our models of planetary formation. Further away, at 398 light-years, lies TIC 887-854-035b. Although very far from the initial limit, this exoplanet attracts attention because its transit is accessible to amateur astronomers equipped with large-diameter telescopes and precise measurement systems. Collective observation allows for higher quality light curves and sometimes the detection of new signals or refinement of known ephemerides. Even at great distances, it raises the same questions. Is it a super-Earth or a mini-Neptune? And is it influenced by other planets? These systems reveal that M and K stars, which are the most common in the Milky Way, often host short orbit planets. Observation campaigns, such as the TESS satellite, are particularly effective on these dimmer targets compared to the Sun, because the luminosity contrast during a transit is more pronounced. The constant improvement of instruments, whether spectrographs or photometric cameras, has considerably increased the number of detections. Even if GJ 2126b and Ross 176b seem uninhabited, they broaden our view of possible worlds and formation scenarios. Super-Earths, which are sized between Earth and Neptune, spark particular interest. Do they possess a metallic core and rocky mantle, or a thick gaseous envelope? TTV and radial velocity measurements help answer these questions. In some cases, data suggest the presence of invisible planets, further complicating the interpretation of observations. Astronomers strive to reconstruct the system's history based on numerous parameters: mass, distance from the star, primordial disk density, stellar rotation, magnetic field. TIC 887-854-035 B illustrates the growing role of amateur astronomers, whose observations can complement those of professionals. Thanks to networks of observers spread across several continents, transit monitoring becomes almost continuous despite day-night cycles and local weather. These 3 planets testify to the diversity and vitality of exoplanetary research. They contribute to a vast cosmic puzzle aimed at understanding how worlds form, migrate, and interact with their star and neighbors. Future generations of telescopes and spectrographs may allow us to one day detect the signature of an atmosphere similar to ours around a distant super-Earth. Let's stop by a region located between 80 and 200 light-years from Earth. It is in this vast space that the Transiting Exoplanet Survey satellite, better known as TESS, made a series of major discoveries in 2025. Designed by the American Space Agency to identify exoplanets by monitoring slight decreases in brightness caused by their passage in front of their star, TESS revealed 5 new worlds in the sphere of red dwarfs: TOI 512b, TOI 771c, TOI 5800b, TOI 2407b, and TOI 2431b. TOI means TESS Object of Interest, in other words, an object of interest identified by TESS. Each of these celestial bodies has radii between 1.1 and 1.6 times that of Earth, placing them in the category of super-Earths or mini-Neptunes. Their environment is extreme because they all orbit very active red dwarfs, subject to a high level of irradiation. To understand the stakes, let's remember that a red dwarf is a star smaller and less luminous than the Sun, classified as type M in the stellar sequence ranging from the hottest to the coldest stars. Less bright, but often very dynamic, they can release frequent stellar flares, bombarding nearby planets with energetic particles and violent radiation. For these 5 worlds, this activity, combined with their proximity to the star, leads to a phenomenon called photoevaporation. The irradiation gradually erodes the atmosphere, especially if it is thin or not very dense. When TESS detected these planets, researchers quickly identified the risk of rapid photoevaporation. A light gaseous envelope could dissipate under extreme rays, leaving the planet bare and potentially exposing a rocky surface. This situation intrigues scientists, who see it as an opportunity to better understand how worlds close to small stars evolve or survive in hostile conditions. Among them, TOI 2431b stands out. Its orbital period is described as ultra-short, approximately 0.22 days, or just over 5 hours. In a tiny amount of time, this small world completes a full orbit around its star, experiencing on its exposed face temperatures estimated at over 1,000 degrees Celsius, capable of melting many Earth materials. For astrophysicists, such an environment offers a unique study field on the extreme effects of stellar proximity. The radii of these 5 planets, ranging from 1.1 to 1.6 times that of Earth, provide information about their potential composition. In this range, some may be rocky with a thin atmosphere, while others have a thicker gaseous envelope, similar to Neptune or Uranus. Discoveries by TESS confirm that these intermediate sizes are common in the universe. The irradiation they undergo is among the most intense known for this type of orbit, making photoevaporation highly probable. By studying the rate of this atmospheric loss, astronomers hope to better understand planetary evolution and determine whether some of these planets retain a residual atmosphere or quickly become devoid of protective gases. To refine these observations, the James Webb Space Telescope, or JWST, will be mobilized. Specialized in infrared, it will be able to detect precise signatures like the presence of helium, notably thanks to the NIRIS instrument, capable of spotting the characteristic line at 10 to 83 nanometers. This signal would indicate an active atmospheric escape and provide a direct clue of the intensity of photoevaporation. Helium is a crucial marker because it is one of the lightest elements, quick to escape if the atmosphere is not very massive or subjected to strong stellar winds. Studying this phenomenon on these 5 planets, with their radii moderately superior to Earth's, offers an ideal laboratory for comparing different degrees of magnetic protection, internal dynamics, and composition. Some of these planets are in short orbits, sometimes gravitationally locked, presenting one side always illuminated and one side in perpetual night. In very active systems, even the nighttime side is not spared by coronal mass ejections. The tidal forces, particularly intense, can increase internal heating and modify the atmosphere. These planetary systems thus act as true laboratories for studying the fate of atmospheres and the potential habitability of extraterrestrial worlds. A planet devoid of protective gas is exposed to lethal conditions for life as we know it. But the scientific interest also lies in improving models of planetary formation and evolution. The research relies heavily on repeated observation of transits. The drops in brightness detected by tests are complemented by radial velocity measurements, allowing the estimation of mass, density, and probable composition. In these high radiation environments, these parameters can evolve over time if the planet loses its atmosphere. Ground-based telescopes also participate in the monitoring of red dwarfs, analyzing their spectrum to spot chemical elements or signs of eruptions. The state of the star directly influences the atmospheric retention of a planet. Long-term observations allow linking stellar activity and planetary evolution. The JWST plays a key role here by scrutinizing the light filtered by the atmosphere during transits, looking for signatures of elements like hydrogen, oxygen, or helium. These signals can vary greatly from year to year, especially for worlds close to very active stars. The flurry of discovery of these 5 planets in 2025 results from TESS's scanning mode, which observes a sector of the sky for a given time before moving to the next. The close detections enable the comparison of worlds sharing similar characteristics: short orbits, strong eruptions, extreme irradiation. The study of these worlds will continue over several years. The initial observations serve to specify orbits, sizes, temperatures, and masses. These are followed by more detailed measurements of the light curve and atmospheric profile. The evolution of photoevaporation is monitored to detect any notable losses. All these planets, although orbiting around red dwarfs, exhibit varied conditions: equilibrium temperature, albedo, distance to the star, or tidal effects influence atmospheric dynamics. Some can exceed 1,000 degrees Celsius, while others are limited to 800, which significantly alters the escape velocity of gases. The main goal is not only to catalog new worlds, but to unravel the mechanisms of planetary survival in an extreme environment. Observations from the JWST will confirm the presence of helium and measure atmospheric erosion. If confirmed, it will demonstrate how these planets' fates are directly shaped by their star. These data will feed simulations aimed at testing various scenarios, such as the impact of stellar rotation on eruption frequency or the evolution of atmospheres over millions of years. Scientists hope to anticipate the moment when a planet might completely lose its gases. There might also be other worlds orbiting at greater distances, less exposed, and more temperate. Future observations could reveal planetary companions that went unnoticed during the initial detection phase. The TESS spree around red dwarfs is just the beginning. The 5 planets discovered in 2025 will serve as a reference for studying rapid evolution under high irradiation. Each spectrum, each light curve, will enrich our understanding of planetary diversity and chart the future lines of exoplanetary research. Let's now direct our attention to a region of space located between 100 and 300 light-years from Earth. On the galactic scale, these distances remain close, forming a broader neighborhood where compact planetary systems, rich in insights, are discovered. 2 targets particularly capture our interest: TOI 1117, which hosts 3 planets slightly smaller than Neptune, and TOI 1453, composed of 2 worlds of intermediate size between Earth and Neptune, orbiting a K-type dwarf star. Each of these systems tells a unique story of planetary formation and evolution. A light year corresponds to the distance light travels in 1 year at about 300,000 kilometers per second. A radius of 100 light years already represents nearly 1,000 trillion kilometers, a gigantic scale for us, but modest on the galactic scale. In this perimeter, observations carried out by various telescopes, including NASA's TESS mission, are essential for cataloging exoplanets. TESS detects tiny variations in star brightness, indicative of a planet passing in front of its star, a phenomenon known as planetary transit. Objects identified as TOI, or TESS Object of Interest, are then studied in detail to confirm their nature. TOI 1117 stands out due to the presence of 3 sub-Neptunes, planets with a radius slightly smaller than Neptune, which is between 2 and 3 times that of Earth. Their internal composition can combine a rocky core and an atmosphere of hydrogen, helium, or water vapor. In this system, each planet orbits very close to its star, completing a full revolution in 2 to 9 Earth days. This proximity results in very high temperatures, well over several hundred degrees Celsius. A notable feature of TOI 1117 is the presence of strong transit timing variations, or TTV. Transit times are not always identical from one cycle to another due to gravitational interactions between the planets. Analyzing these variations allows scientists to estimate the mass of each planet, refine the configuration of the orbits, and sometimes reveal previously unknown objects. These TTVs are a valuable tool for probing the internal dynamics of a planetary system. The planets of TOI 1117 might be linked by orbital ratios close to whole numbers, a phenomenon called resonance. In these configurations, gravitational interactions repeat regularly, sometimes stabilizing the whole system. Even though the dynamics of TOI 1117 are complex, these constant interactions partly explain the observed TTVs. TOI 1453, located at a similar distance, also draws attention. This system orbits a K-dwarf, cooler and smaller than the Sun, but more massive and warmer than an M-dwarf. Its surface temperature ranges between 3,000 and 5,500 degrees Celsius, and its moderate brightness facilitates the study of its planets. 2 of them, named AB and AC, measure approximately 1.9 times the Earth's radius, placing them in the super-Earth or mini-Neptune category. Their position allows both their mass and radius to be determined through radial velocity measurements and transit observations. Deducing their average density provides clues about their composition, whether metallic, rocky, aqueous, or gaseous. However, measuring the mass of planets around dim stars remains challenging. Radial velocity variations are weak and require instruments of extreme precision. Recent advances, however, allow for the detection of signals equivalent to a few tens of centimeters per second, opening the way to studying increasingly smaller planets. The interest in TOI 1453 also lies in the possibility that it represents a population of intermediate worlds, useful for testing models that describe the end of planetary accretion. According to these theories, materials from the protoplanetary disk assemble into protoplanets that sometimes migrate inward or outward, influenced by the density and temperature of the disk. Small stars like K and M dwarfs can thus generate very compact systems. These systems challenge the classical solar system scheme, where rocky planets are close to the star and gas giants farther away. In many examples, several intermediate planets orbit very closely. Observing these architectures informs us about planetary migration and the redistribution of planets shortly after their formation. The last phase of accretion gathers the remaining debris around the planets. If a planet grows rapidly, it can attract a thick, gaseous atmosphere, becoming either a giant or a sub-Neptune depending on the conditions. The final arrangement results from a balance between migrations inward or outward. The study of TOI 1453, with its 2 close planets, offers an ideal test for these scenarios. These compact systems also offer opportunities to analyze the atmosphere of planets via transit spectroscopy. When the star's light passes through the planetary atmosphere, certain wavelengths are absorbed, revealing the presence of molecules such as water vapor, carbon dioxide, or methane. Despite their high irradiation, it remains possible to detect such signatures, especially if the star is not too bright. Located at a relatively close distance, TOI 1117 and TOI 1453 belong to a sample of objects that allow for the accumulation of comparative data, essential for establishing an exoplanet atlas. This statistical approach, combining precise measurements and simulations, allows testing the validity of theoretical models and adjusting our assumptions when observations contradict them. The combined study of radial velocities in TTV offers a complete view of the masses, orbits, and planetary interactions. Multi-planet systems, although more complex to analyze, provide valuable constraints, making their study particularly rich. These intermediate worlds, absent in our solar system, seem nonetheless very common in the galaxy. Knowing them better is thus essential, as their abundance could mean they represent the most common form of planet. This raises the question of their potential to harbor life, even if hot sub-Neptunes are probably too scorching for that. In this quest, observation and theory advance together. Different formation scenarios involve varied initial conditions and multiple migratory processes. Resonances, inclinations, and densities are clues that help differentiate these hypotheses. Thus, the area located between 100 and 300 light-years abounds with compact systems where intermediate planets interact closely, producing valuable dynamic signatures. Just as explorers of old charted new lands, astronomers today are mapping the planetary architectures of the Milky Way. By observing TOI 1117, we discover a trio of fast-orbiting sub-Neptunes, whose TTV reveals their interactions. By studying TOI 1453, we see how two similarly sized planets refine our understanding of their composition. Together, these systems illustrate the transition from exploratory exoplanetology to comparative science, where each discovery fits into a broader framework. Although the question of life is not central here, these studies contribute to understanding all stages of planetary evolution. The data from these small, compact systems enriches collective knowledge, gradually building an edifice of understanding. By examining TOI 1117 and TOI 1453, we test our formation models and again find that nature, in its inventiveness, far exceeds our predictions. At the heart of a vast cosmic zone, located between 120 and 350 light-years from our solar system, is an array of fascinating destinations for astronomers and astrophysicists. Here, we encounter several stellar systems, notable for the presence of protoplanetary disks and giant planets still forming or newly born. In this area of space, scientists exploit the observational power of the James Webb Space Telescope, or JWST, to precisely study the birth and evolution of gaseous worlds. Among the most captivating targets are TWA-7b, MP Muskie b, and HD 135344-AB, each revealing a different facet of planetary formation in a dust-saturated environment. A technology has revolutionized research in this zone located between 120 and 350 light-years, direct imaging. To detect planets around other stars, several methods are used, such as radial velocity measurements or detecting luminosity variations during transits. But direct imaging stands out by allowing the analysis of a planet's own light, as well as the structure of the surrounding gas and dust disk. Thanks to its sensitive infrared instruments, the James Webb Space Telescope distinguishes the residual heat of a young planet. Ordinarily, a star's brightness renders its planets invisible, but adaptive optics and coronagraphy techniques, which block stellar light, now provide a clear view of their environment. For TWA-7b, this method enabled, for the first time with James Webb, a direct image where the planet appears distinctly at the center of a protoplanetary disk with 3 rings. This major advancement opens the possibility of observing both a planet and its immediate environment simultaneously, which remains rare with other approaches. To understand the scientific interest of TWA-7b, one must first look at what a protoplanetary disk is. Imagine a forming star at the center of a vast, rotating cloud of gas and dust. Under the influence of gravity, this cloud collapses on itself, forming an incandescent core that will become a star, while the remaining material organizes into a flat disk. In this disk, particles, molecules, and small solid bodies collide and aggregate, giving birth to planets. In the case of TWA-7b, James Webb revealed 3 concentric dust rings surrounding the host star, areas where density and temperature vary. TWA-7b, whose mass would be comparable to Saturn's, orbits within or near these rings, drawing from this reservoir of material to continue its growth. Observing a planet in such an environment is essential to understand the physics of giant world formation, interactions with the disk, gravitational influence, dust grain dynamics, and possible satellite formation around the planet. Other intriguing targets also emerge thanks to direct imaging in this region up to 350 light-years away. MP Musca b, located about 319 light-years away, is developing around a young T Tauri-type star characterized by intense magnetic activity, powerful stellar winds, and a disk rich in gas and dust. This giant planet, probably more massive than Saturn, is still forming in a dense disk. The star, a true stellar factory, complicates the analysis of the disk with its activity. Researchers use astrometry and study of the disk's kinematics to understand how the planet modifies the dynamics of the surrounding matter. This near real-time monitoring offers a rare glimpse into the interactions between a growing giant and its protoplanetary cradle, allowing direct comparison of theoretical models with observations. Let's continue with HD 135344, AB, a giant detected around a young star located about 440 light-years away. The first confirmed planet in this system, it orbits a star more massive than a T Tauri, whose protoplanetary disk already shows cavities and dust arms, signs of the action of a forming planet. The age of this star does not exceed a few million years. Thanks to the Sphere instrument, which blocks stellar light and detects the faint glow emitted or reflected by the planet, astronomers have been able to observe these structures. Combined with astrometry and study of the disk, these data reveal a gas giant actively interacting with its environment, offering a key piece of the planetary genesis puzzle. These systems, TWA-7, MP Muscae, and HD 135344, are true living laboratories. The planets they harbor are observed at the very moment of their formation, still immersed in their disks. Measurements of dust distribution, gas chemistry, and temperatures allow us to pinpoint the conditions that accelerate or slow the formation of gas giants. The data also shed light on the history of our own solar system, whose Jupiter and Saturn probably emerged in a similar disk over 4 billion years ago. The James Webb plays a central role in these discoveries. From space, it escapes the atmospheric turbulence that limits terrestrial observations, capturing infrared light with unmatched precision. It detects spectral signatures of elements like water or carbon monoxide, which are difficult to observe from the ground, and thus reveals the composition and dynamics of the disks, even the birth of future moons. TWA-7b will remain the first direct image of this type made by Webb, but certainly not the last, as observation programs multiply. These worlds pose major questions. When does a disk stop feeding a planet? Why do some plunge into the heart of the disk while others remain at a distance? Could some be formed by gravitational instability without going through the solid core phase? Current data helps distinguish between these scenarios, for example, by measuring the remaining gas mass and comparing it to that of the planet to estimate the growth duration. Spiral structures or gaps in the disk also reveal the strength of the disturbances exerted by the planet, refining formation models. The long-term evolution of these giants remains another issue. Over time, some migrate towards their star or move away from it, or are even ejected from the system. For now, TWA-7b, MP Muscae b, and HD 135344 AB seem stable, but future observation campaigns will follow their trajectories to learn more. Let's head to a rare and fascinating system, a planet that orbits two stars, located about 400 light-years from Earth. This place alone evokes the wonder of astronomy enthusiasts. Its codename is Bebop 3b, the first circumbinary world identified in 2025. A circumbinary world does not orbit an isolated star but a stellar pair. Instead of a single source of light and heat, the planet revolves around two suns that orbit each other. This configuration recalls the iconic double sunset of science fiction, but in reality, it remains difficult to detect. Classic methods, such as radial velocity or transits, become much more complex when two stars simultaneously disturb the received light. Bebop 3. B is particularly intriguing because it allows for direct observation of the gravitational dance of a world completing a full orbit of its two suns in 547 days, which is a little less than a year and a half on Earth. Its orbit, with an eccentricity of 44/100ths, is distinctly elliptical. This shape causes periodic variations in distance relative to the center of gravity of the system. The closer it is, the more light and heat the planet receives. The farther it is, the less it receives. If it has an atmosphere, these variations could lead to more extreme climatic cycles than on Earth. Its composition, gaseous or rocky, remains unknown, but upcoming telescopes should shed light on this question. To detect such a world, astronomers had to contend with the complexity of transits in a double system. The planet can pass in front of either star, or its transit can be masked by an eclipse between them. Despite these challenges, a clear signal was isolated, confirming that Bebop 3b indeed orbits both stars. Radial velocity, measuring the tiny movement variations of stars due to the planetary mass, helped complete these observations, although its use is delicate in this context. It remains to be understood how this planet maintains a stable orbit. The laws of celestial mechanics impose a minimum distance beyond which a circumbinary orbit becomes viable. Here, despite its eccentricity, Bebop 3b stays out of the unstable zone. Simulations suggest long-term stability, but researchers will continue to verify whether, over millions of years, the orbit might change. Circumbinary worlds are invaluable for refining planetary formation models. In simple systems, planets are born from a single disk of gas and dust. In binary systems, gravitational forces profoundly alter the distribution of matter. Bebop 3b may have formed in its current location or migrated from a more distant zone. The evolution of the two stars is another crucial factor. Their brightness and activity can reshape the conditions around the planet. Future observations will aim to determine precisely their brightness, temperature, and spectral class. Regarding the possible climate, everything depends on the nature of the planet. If it is gaseous, the light variations could create complex atmospheric dynamics with powerful winds and thermal cycles. If it is rocky, its surface might experience significant thermal expansions. Current instruments cannot yet decide, but future infrared telescopes might identify the chemical composition of its atmosphere, if it exists. Beyond scientific curiosity, Bebop 3b tests our theoretical models. Its eccentricity could cause internal heating through tidal effects, potentially influencing its geological activity, as is the case with some of Jupiter's moons. The Plato mission, launched by the European Space Agency, will play an essential role in its monitoring. This space telescope will observe vast stellar fields over long periods, accurately identifying transits and analyzing star oscillations to refine our knowledge of their characteristics and, indirectly, of the planet. Prolonged tracking is necessary to confirm the orbital parameters of Bebop 3b, detect any changes in eccentricity, or identify the presence of other bodies. Each new circumbinary planet broadens our view of possible architectures. Before these discoveries, such worlds were believed improbable, if not impossible. Yet, Bebop 3b proves that planets can sustainably evolve in complex environments. A world with two suns also offers fertile ground for imagination. Multiple sunrises and sunsets, regional variations in light and heat, seasons dictated by stellar choreography. Measuring these thermal contrasts would be fascinating, even if current technology does not yet fully allow it. Its dynamic stability, confirmed by detailed simulations, makes it a rare case. It also offers the opportunity to test planetary migration scenarios and perhaps discover other companions in this system. Plato, with the support of new generation ground-based telescopes, will be able to refine the measurement of its radius, its eccentricity, and, if possible, the composition of its atmosphere. 400 light-years away from us, Bebop 3b embodies the complexity and beauty of circumbinary systems. It questions the formation, stability, and evolution of planets in a two-star environment and could become a crucial milestone in understanding the diversity of worlds. It is not just a point on a celestial map. It is a pioneer, a daring planet that challenges the limits of our knowledge and nurtures the idea that, sometimes, reality surpasses fiction. Situated between roughly 400 and 800 light-years from our solar system, a group of giant gas planets revolves around stars, undergoing transformation towards subgiant or giant states. In this distant zone, several stars have already left the main sequence, the stable phase of their existence lasting billions of years. They then begin to expand and increase their luminosity, initiating a process that profoundly alters their nearby environment. Within this cosmic landscape, certain particularly remarkable targets capture the researchers' attention as they provide valuable clues regarding the mechanisms of planetary migration and atmospheric evolution around changing stars. Among these worlds, the stars HD 87816, HD 94890, and HD Penso 2888 stand out. Each hosts at least one giant gas planet, if not several, whose mass varies between 6 and 12 times that of Jupiter. These planets are much more massive than those observed around stars like our Sun, even though they receive less media attention than smaller planets. These impressive objects, often called superjupiters or massive gas giants, provide essential insights into how these worlds react to the increase in stellar luminosity and the chemical transformation of their atmosphere under rising radiation. In the case of HD 87816, observations reveal two planets provisionally named B and C, evolving between 1 and 4 astronomical units from their star. An astronomical unit corresponds to the average distance between Earth and the Sun, roughly 150 million kilometers. These distances suggest a warm, but not extreme zone when the star is similar to our Sun. However, for a star becoming a subgiant or giant, its temperature and luminosity can exceed that of our Sun, increasing the energy received by the planet. This surplus heats its upper layers and can swell its atmosphere, a phenomenon observed in several specialized studies. The HD 87816 system particularly captures scientists' attention because it illustrates different phases of transformation of these giant gas planets. The closest planet, with a mass between 6 and 12 times that of Jupiter, undergoes an intense bombardment of energetic particles emitted by a star more luminous than a mature Sun. These particles penetrate the high atmosphere, causing a temperature rise, its expansion, and sometimes the loss of light gases. This process, called atmospheric inflation, represents an increase in the actual radius of the planet compared to a similar giant orbiting a less bright star. In the same region, HD 94890 also presents two planets, designated B and C, evolving between 1 and several astronomical units from their star. This system constitutes an ideal laboratory for studying planetary migration. Giant gas planets often form far from their star, in regions rich in ice and volatiles. Over time, some migrate inward in the system under the effect of gravitational interactions or massive neighboring bodies. When the star expands and evolves, the internal dynamics of the system change, further influencing the final migration of the giants toward closer orbits. In this context, the high atmosphere of these planets can reach several hundred degrees Celsius, sometimes between 500 and 1,000 degrees, even with a significant mass. For comparison, Jupiter and Saturn have much lower temperatures in their upper envelopes. These inflated giants experience high temperatures in their outer layers, affecting the atmospheric chemistry. Molecules like water, methane, or other complex species can be dissociated, making the atmosphere rich in exotic compounds. Further away, HD 102888 has at least one gas giant, named HD 102888b, whose mass is also estimated to be between 6 and 12 times that of Jupiter, orbiting at a few astronomical units. This star illustrates the diversity of mechanisms to which these worlds are subjected when facing a star transitioning into a subgiant or red giant. This transformation is accompanied by an increase in luminosity, an extension of the outer layers, and possibly an increase in the magnetic field, which is still poorly understood. During the star's expansion stage, the habitable zone moves farther away. That is, the region where liquid water could exist on a solid surface. For gas giants, this concept is adapted because they do not have a solid surface. However, if one of them has satellites, it is conceivable that one could be in a region conducive to liquid water. Theoretical studies on these moons are gaining traction, as they could be habitable if their orbit is adequate, and they escape destructive effects like excessive heating or too strong tidal forces. Beyond the search for favorable conditions for life, the observation of these evolved systems sheds light on a fundamental process: the migration of massive planets. Over the lifetime of a star, these orbital shifts can occur over millions of years or throughout the star's entire growth. When the subgiant expands and prepares for new nuclear reactions, the redistribution of its internal mass alters its gravitational field. This evolution influences the planet, which can stabilize or tighten its orbit. Understanding these stages is crucial for reconstructing the history of the system and anticipating its future, especially when the star reaches the advanced stage of a red giant. Atmospheric inflation partly results from the thermal constraints imposed by the expanding star. The energy it emits increases in the visible, infrared, and ultraviolet spectra, depending on its temperature. The surface of a subgiant may remain close to that of a younger star or rise slightly, but its large size and the low density of its outer layers produce intense radiation. For planetary atmospheres, this means increased absorption in the upper layers, where the density is low. These layers expand, becoming more vulnerable to the escape of hydrogen and helium, the main components of gas giants. Over time, these losses leave a chemical signature visible in the planet's spectrum. Modern instruments, stemming from ancient space missions or recent prototypes, closely study these evolved giants. The analysis of transmission radiation, starlight filtered through the planetary atmosphere when passing in front of the star, allows the detection of specific gases. Water vapor, carbon oxides, and other molecules reveal the composition and atmospheric structure. Moreover, the radiation emitted by the planet offers clues about its internal temperature, possible clouds, and its formation history. These high-precision methods make it possible to paint a detailed portrait of these massive giants likely to expand further with their star's evolution. In parallel, HD 87816, HD 94890, and HD 102888 are key examples for analyzing the influence of a more massive or older star on the stability of its planetary entourage. Tidal interactions can slow the rotation of the star or the planet, or even lead to the engulfment of the latter if its orbit comes too close to the stellar surface. Current simulations seek to model these phenomena and estimate that many gas giants around stars in the red giant phase will end up engulfed, while others will maintain a more distant, stable orbit. It also happens that the planet influences the star. The tides it generates extract energy or angular momentum from the system, which can slow down or accelerate certain internal processes depending on the relative mass and distance. The discovery of the planets HD 87816b and C, HD 94890b and C, and HD 102888b offers a valuable sample for studying these reciprocal interactions. Each planet-star pair or trio presents a unique configuration, modulating the balance between radiation, gravity, tides, and orbital dynamics. Observing the evolution of these systems in the coming years promises to reveal the mechanisms at work when a gas giant undergoes the effects of an expanding star. Distances ranging from 400 to 800 light-years pose observational challenges. Yet, these systems are closer than other similar ones located several thousand light-years away. This proximity facilitates spectroscopic studies and the characterization of stellar parameters. These stars, slightly more luminous than our Sun, are prime targets for measuring the mass and radius of planets, as well as the evolution of their orbits. With the new generation of ground-based telescopes and dedicated space missions, each year enriches our understanding of these unique worlds. When discussing distant giant planets orbiting stars other than the Sun, the image of vast gaseous bodies like Jupiter or Saturn often comes to mind. However, a particular type of planet has been prominent in astronomy for several years: hot Jupiters. These planets, similar in size to Jupiter, orbit very close to their star, completing a full orbit in just a few days, sometimes less than a week. Their exposure to intense radiation raises their temperature well beyond 1500 degrees Celsius. This extreme heat strongly influences their atmosphere, altering its composition and the distribution of gases around them. The missions TESS, an acronym for Transiting Exoplanet Survey Satellite, and WASP, for Wide-Angle Search for Planets, have revealed several of these scorching worlds located between 700 and 1500 light-years from Earth. To understand the significance of these discoveries, one must first understand the method used. TESS and WASP detect tiny drops in brightness caused when a planet passes in front of its star, a phenomenon called planetary transit. During this passage, the light receives slightly decreases. By analyzing the duration and intensity of this drop, researchers determine the size of the planet and the length of its orbital period. Sometimes, they also estimate its equilibrium temperature, which depends on its distance from the star and the energy emitted by it. In the case of hot Jupiters, orbital periods generally range between 3 and 6 days, indicating their proximity to their star. This proximity results in temperatures exceeding 1500 degrees Celsius, plunging the atmosphere into an extreme state. Water molecules, methane, and other rarer compounds become highly excited, and some may dissociate due to intense radiation. This closeness also generates significant tidal forces, influencing the planet's rotation. Frequently, this rotation aligns with the orbital period, just as the Moon always shows the same face to Earth. Thus, one hemisphere remains constantly exposed to radiation, while the other stays in shadow. Among the most representative examples are 4 hot Jupiters identified in this zone: WASP 154b, WASP 188ab, WASP 195b, and WASP 197b. Their detection relies on careful observation of the brightness drops of their respective stars. These planets all have a short orbital period of 3 to 6 days, placing them among the closest to their star. Their atmospheres reach temperatures above 1500 degrees Celsius, making them prime targets for studying extreme phenomena: rapid atmospheric winds, the formation of silicate clouds, and uneven heat distribution between the illuminated and dark sides. To understand the notion of harvest in this context, it is important to remember that the TESS mission is designed to explore a vast portion of the sky in search of transiting exoplanets. It complements the data from WASP, an older but still active program. This synergy allows for the regular discovery of new planets, especially hot Jupiters, due to the significant size of their transit and their short orbital period, easily detectable through photometric measurements. The arrival of recent instruments like MIRI on the James Webb Space Telescope opens new perspectives. This instrument observes in the mid-infrared, a crucial range for analyzing the chemical composition of high-temperature atmospheres. By studying the light emitted or reflected at different orbital phases, astronomers identify the presence of molecules such as water, carbon monoxide, or carbon dioxide. The phenomenon of thermal phase inversion appears when there is a strong temperature difference between the day side and the night side. Measuring these variations in the structure of atmospheric layers is essential for understanding wind circulation. For some hot Jupiters, the side facing the star can reach such a high temperature that it reverses the usual temperature variation with altitude. Generally, the temperature decreases with altitude, but intense absorption of ultraviolet or infrared radiation can heat the upper layers, causing a thermal inversion. These extreme conditions provide a privileged study ground to refine atmospheric models, particularly on heat redistribution by winds or the formation of clouds composed of exotic elements. Let's take the example of WASP 154b, located about 1,000 light-years away. Despite its size comparable to Jupiter, it orbits in a few days and receives a much more intense stellar flux than Jupiter. Models predict a very high equilibrium temperature, suggesting almost constant irradiation of its daytime hemisphere. The nighttime side, on the other hand, could be significantly cooler if winds do not effectively redistribute the heat. This thermal difference raises questions about atmospheric transitions, the circulation of violent winds, and the stability of molecules in the atmosphere. WASP 188, AB, belonging to a binary star system, orbits the primary star designated A, hence the presence of this letter in its name. Also detected by the transit method, this planet orbits in 4 to 5 days, with an equilibrium temperature exceeding 1,500 degrees Celsius. Astronomers hope that future observations with MIRI will reveal more information about the structure of its atmosphere and the light interactions between the planet and its star. WASP 195b, also in this distance range, offers the opportunity to study several hot Jupiters in various stellar environments. Each star emits a specific light spectrum according to its temperature and size. Thus, two planets receiving a similar flux may absorb light differently depending on their host star. This subtlety fascinates astrophysicists who seek to understand chemical variations, planetary mass, and wind dynamics. By combining observations of transits and secondary eclipses, they measure the radiation emitted by the planet, detect the presence of essential gases, and reveal the potential presence of unusual molecular clouds. Finally, WASP 197b completes this series of short-period giants. Its equilibrium temperature also exceeds 1,500 degrees Celsius. At these temperatures, some metallic compounds can vaporize and then condense further in the atmosphere, particularly at the boundary between the illuminated and dark side. These worlds offer a unique opportunity to study the resilience of various molecules under extreme conditions. Atmospheric chemistry differs between layers exposed to radiation and those shielded from light, with more fragile chemical species able to survive in shaded areas. The simultaneous study of these 4 hot Jupiters allows identifying notable similarities and differences. The first question concerns their formation. These gas giants likely form at a greater distance, then migrate inward under the effect of gravitational interactions with the protoplanetary disk or other planets. This migration partly explains the diversity of observed orbits. The second question concerns the atmospheric structure. Beyond the high daytime temperature, researchers are interested in the pressure in the deep layers, the opacity rate affecting the light traversing the atmosphere, and the possible presence of clouds of silicates, oxides, or metals. Modeling these atmospheres requires understanding how molecules decompose and reform according to temperature. For example, water can dissociate into atomic hydrogen and oxygen, then recombine on the nighttime side, affecting the planet's thermal emission. The James Webb's MIRI instrument, operating in the mid-infrared, is ideal for analyzing these phenomena. Its sensitivity allows detecting minimal flux variations during eclipses or transits. These measurements facilitate the search for complex molecules and study of thermal inversion, revealing which atmospheric layers are hottest and how chemistry evolves with altitude. The term thermal phase inversion laboratory describes these planets as a perfect testing ground for this phenomenon. When the planet passes in front of its star, it partially dims the star's light. When it disappears behind it, we measure the flux emitted by the planet itself, thus detecting thermal inversion signatures in the emission spectra. Cases like WASP 154b or WASP 195b could reveal marked inversions. At these temperatures, compounds such as titanium monoxide or vanadium in gaseous form absorb radiation, heating the upper layers of the atmosphere. This thermal profile, where the outer layer is warmer than the lower layers, contrasts with that of more temperate planets. Under extreme conditions, some metals can even form clouds at specific altitudes, although their formation remains a subject of active research. Beyond chemistry, the study of hot Jupiters sheds light on the dynamics of planetary systems. The discovery of several giant planets in transit, located between 700 and 1,500 light-years away, allows us to examine their sizes, masses, compositions, and stellar proximities. Researchers evaluate whether migration follows a common pattern or if each system evolves differently. Some hot Jupiters evolve in multiplanetary systems, complicating their trajectory and orbital stability. The speed of their revolution facilitates their observation, with several transits or eclipses being collectible in just a few days. This frequency improves the precision of mass and radius measurements. The transit method provides the radius, while the radial velocity technique detects the star's oscillations under the gravitational influence of the planet. The more massive and closer the planet is, the stronger this signal. The combination of both methods gives the overall density, offering clues about the internal structure. The search for chemical signatures completes these analyses. It allows for a better understanding of the impact of temperature on molecular distribution, cloud formation, and circulation between the day side and the night side. Models attempt to predict wind speeds, jet stream formation, and chemical variation according to longitude. Data from the 4 hot Jupiters enrich these models, helping to confirm or refute certain hypotheses. Beyond the scientific aspect, the observation of hot Jupiters also captivates the general public. The image of a giant boiling planet orbiting its star in just a few days fascinates. These worlds with changing skies, with one side constantly illuminated and the other plunged into darkness, evoke an infernal weather. For astronomers, it's an opportunity to clearly explain detection methods and spectral analysis, especially with powerful instruments like the James Webb. Finally, these burning worlds illustrate the richness and diversity of the planets in the Milky Way. For a long time, exobiologists have focused on terrestrial planets to search for life. Even though hot Jupiters are not conducive to life, studying them is essential to understand atmospheric physics, migration, and planetary formation. The ability to measure their composition precisely with MIRI opens up a better understanding not only of these nearby giants, but also of other planetary types beyond our system. In the coming years, the James Webb plans several observation campaigns dedicated to promising exoplanets, notably from TESS and WASP. Near and mid-infrared spectroscopies will reveal molecular fingerprints in the atmosphere. Depending on the results, the hypothesis of thermal inversion can be confirmed or refuted. These very hot giants will remain a perfect laboratory for advancing the understanding of opacity, the effects of extreme radiation, and thermal distribution. Beyond 1,000 light-years, and up to distances reaching 3,500 light-years from Earth, stretches a mosaic of exoplanets revealed by the Kepler and K2 space missions. At this scale, discoveries are rarer than in the sectors close to our Sun, as the light from distant stars is harder to capture. Yet, thanks to detection instruments developed over the past 10 years, several intriguing planetary systems have been observed and studied in this remote region of the galaxy. These discoveries form what astronomers sometimes call the refined legacy of Kepler and K2, a collection of worlds that enrich our understanding of planetary architectures beyond more classic examples. First, let us recall the principles that have enabled the detection of these distant planets. The Kepler and K2 missions measure the very slight reduction in a star's brightness when a planet passes in front of it. This phenomenon is called the transit method. If an exoplanet occults a tiny portion of the stellar disk, the light curve recorded by the telescope shows a subtle decrease. By analyzing the frequency and magnitude of these repeated dimmings, astronomers can deduce the planet's orbital period, its approximate radius, and other characteristics of its orbit. For particularly distant systems, The signals are often weaker because the stars are dimmer and further away. Despite this, advanced algorithms manage to extract numerous clues later confirmed by other techniques, such as the radial velocity method, which measures the tiny oscillations of a star's velocity around its center of gravity. Let us now explore the first notable planet in this region, Kepler 725c. This planet arouses particular interest because recent studies attributed a mass estimated at nearly 10 times that of Earth, making it a massive super-Earth. This estimate is based on the combination of Kepler light curves and follow-up observations made from ground-based observatories to assess gravitational effects on its star and sometimes on other planets in the system. Specialists place it in the so-called optimistic zone, a semi-habitable range that could allow the presence of liquid water under certain conditions. The term optimistic means that the planet is close to the edge of the habitable zone, where the surface temperature could remain between 0 and just over 100 degrees Celsius, according to current models. These hypotheses, however, remain to be confirmed as several parameters influence the planetary climate, starting with atmospheric composition. A planet of this mass can develop a more pronounced greenhouse effect or, on the contrary, maintain a gaseous structure different from that of a lighter planet. Kepler 725c is thus a remarkable laboratory for understanding how mass influences the possibility of a temperate environment or even the beginnings of a hydrological cycle if water is present. Next is Kepler 279e, distinguished by a longer and more eccentric orbit. During the initial surveys, several planets were discovered in this system. Kepler 279e occupies a unique position because it completes its revolution over a significantly longer period than many of its twins detected by Kepler. This type of long trajectory allows for probing outer orbital zones, comparable to where the giants of our solar system evolve. To observe planets analogous to Jupiter or Saturn, one must study orbital periods of several years, sometimes several decades. The period of Kepler 279e far exceeds that of planets close to its star, providing clues about the global structuring of the disk of matter that gave birth to the system. Some models suggest that planetary migrations have pushed certain planets outward. The detailed study of Kepler 279e, therefore, contributes to defining the range of possible planetary formation scenarios, particularly by comparison with worlds closer to the star. Let's now venture into the orbit of Kepler 289e. Discovered after planets B, C, and D of the same system, this planet has highlighted particularly interesting orbital resonances. Astronomers suspect a partial synchronization between its periods of revolution and those of its neighbors. When two planets are in a 3-to-2 resonance, it means that every time one completes 3 revolutions, the other completes 2. This gravitational configuration favors long-term stability while revealing possible mutual perturbations if a third body intervenes. A 2-to-1 resonance implies that one planet orbits twice while the other completes one orbit in the same time frame. This rarer type of resonance can evolve according to various parameters, such as the presence of residual gas or the influence of a more massive planet. The discovery of Kepler 289e enriches the orbital puzzle. By reconstructing the overall dance, researchers refine the chain formation models of planets in the first million years following the birth of the star. Observing these resonances allows for the selection of certain accretion scenarios, such as migration in a gaseous disk or tidal interactions close to the star. In the same logic, the Kepler telescope and its successor K2 have discovered another surprising system, K2-157, which hosts at least 2 planets, K2-157c and K2-157d. The host star is even more distant, making characterization of the planets challenging. The data suggests these worlds have a radius between that of Earth and double. They thus fall within the transition range between terrestrial planets and small gaseous planets called sub-Neptunes. It is precisely around 1 to 2 Earth radii that the balance between a rocky world devoid of a thick gaseous envelope and an object capable of retaining a hydrogen and helium atmosphere plays out. This boundary influences climate, surface pressure, geology, and therefore potential habitability. Density measurements, obtained by cross-referencing transit data and radial velocities, help distinguish a rocky world from a mini-gaseous planet. The significant distance complicates these measurements, but future more sensitive instruments could provide clearer insights. Another fascinating question concerns the nature of host stars, often less known than those closer. When we talk about solar-type analog architectures, we refer to stars close to the Sun in size, temperature, and magnetic activity, likely to host planets with orbits comparable to Mercury, Venus, Earth, and Mars. Astronomers are particularly interested in long-term stability, as certain orbital resonances can avoid collisions or ejections. In a system like Kepler-289, the confirmation of a 3-2 resonance would indicate a self-regulation mechanism protecting the overall configuration. Similarly, 2-1 resonances can provide insights into the reorganization of the protoplanetary disk. Each newly identified exoplanet refines planetary formation scenarios. A world like Kepler-725c, with its significant mass, can mimic or diverge from the Jupiter scheme depending on the presence of other giant companions. It should also be noted that the notion of a long period is relative. Observation instruments designed for missions lasting a few years prioritize systems with short orbital periods, which are easier to observe thanks to several close transits. Detecting a planet taking about a decade to orbit requires several years of data. The Kepler mission has identified long-period candidates not visible during the first year. Kepler-279e is an example, requiring patience and accumulation of measurements to confirm several spaced transits. Astronomers continue to reanalyze data, thus clarifying uncertain orbits. The legacy of Kepler and K2 evolves continually, enriching the catalog of exoplanets located more than 1,000 light-years away each year. Ground tracking plays a crucial role. Telescopes distributed across Earth observe the same stars as Kepler and K2 to confirm candidate planets and refine their orbital parameters. A close binary star or stellar variability can skew initial detections. Researchers use large-diameter optical and infrared telescopes to detect possible stellar image duplications or precisely measure radial velocities. Kepler-725c, Kepler-279e, Kepler-289e, and K2-157c and d underwent this rigorous check before validation. Successive confirmations strengthen the robustness of detections. Sometimes, the estimated mass of an exoplanet needs to be reassessed after adjustments or additional observations. Studying these distant worlds is thus a collaborative effort combining space and ground observations. Let's clarify the importance of orbital resonances. Imagine two planets around the same star, which exert mutual gravitational attraction influencing their speed, orbital energy, or orbit axis. When their periods are close to small whole numbers, for example, 3 orbits for one against 2 for the other, these regular interactions accumulate. Over thousands or millions of years, they can stabilize or destabilize a system. 3-2 resonances sometimes act as a brake or guide, maintaining stable ratios. This phenomenon exists in our solar system, notably between Pluto and Neptune. Exoplanets exhibiting this ratio indicate migrations that occurred during their formation when a protoplanetary disk slowed or accelerated the planets until bringing them into resonance. This facilitates coexistence with minimal disturbances and can persist after the disk dissipates. 2-1 resonances are another example. When the inner planet completes 2 cycles, the outer completes only 1. This configuration often provokes more pronounced interactions and can break more easily, leading to orbital rearrangements, collisions, or ejections. In Kepler-289 or K2-157, some planetary pairs could be approaching this resonance, but this requires further in-depth studies. Discrepancies observed in transit curves and stellar rotation need to be analyzed to understand whether these systems are at the beginning of a reorganization or in a phase of lasting stability. Another notable point concerns the possibility of thick atmospheres on moderately sized planets. If Kepler-725c has 10 times the mass of Earth, it may have retained a significant gaseous envelope. Analyzing its atmospheric spectrum is a major challenge due to the distance and low magnitude. However, Future missions or a next-generation space telescope could scrutinize these worlds. Would we discover traces of water vapor or other molecules? Would we better understand how a planet of this size cools down or heats up? In an environment ranging from 0 to a few hundred degrees Celsius, atmospheric chemistry could be dynamic, perhaps even temporarily allowing liquids on the surface. Each hypothesis remains speculative, but hope rests on technological advancements. The implications for a solar analog architecture type are multiple. If several Earth-mass planets are detected at different distances, we can draw a parallel with Mercury, Venus, Earth, and Mars. The presence or absence of gas giants at intermediate distances, similar to Jupiter or Saturn, will influence the overall stability. In our solar system, Jupiter and Saturn have largely structured the planetary entourage. There might be an equivalent in some distant systems observed by Kepler and K2, favoring or disrupting the inner zone. Astronomers scrutinize irregular transits and radial velocity variations to spot these giants. With missions limited to 4 or 5 years, spotting a planet with a period exceeding 10 years remains a challenge. Extending observations with other tools is essential to identify worlds with wide orbits, shedding light on the global architecture. Finally, a larger-scale statistical analysis is crucial. Kepler-279, Kepler-289, and K2-157 are not isolated. They are part of a sample of more than 2,000 multiple systems discovered by Kepler and K2. Researchers compare these data to identify trends. Do planets form in tight clusters or spread out structures? Is the habitable zone often empty, or do we find super-Earths there? Which resonances dominate? Answering these questions with aggregated data allows testing planetary formation theories. For example, an underrepresentation of the 2-to-1 resonance compared to 3-to-2 may indicate stability preferences. Observing older stars or different spectral types could also change these conceptions. More massive stars or light dwarfs may not form their planets like the Sun. Over time, some initially cataloged systems turn out to be more complex. New planets are discovered or orbits revised. Kepler-289e was detected after the fact, thanks to subtle variations in transit times caused by the inner planets. These transit time variations sometimes reveal additional planets. Thus, the exoplanetary universe is not a static postcard album, but a changing panorama that is refined and enriched each year with new analyses. The Kepler and K2 missions have played a major role by providing a colossal dataset covering vast portions of the sky. Even though these missions are over, their legacy still fuels research. By re-examining old records or cross-referencing them with other probes like TESS, scientists regularly discover new planetary treasures. In the heart of the immense diversity of worlds that populate our galaxy, some planets astonish with their extravagance and fragility. This part invites us to explore the so-called disintegrating or ultra-short orbit exoplanets. These terms reflect extreme physical conditions, unimaginable heat, intense gravitational forces, and permanent erosion of planetary structures. Among them, 2 cases stand out. BD plus Osavari 5, 4868 AB, with its comet-like tail formed of rocky particles, and TOI 2T431b, whose life will extend only over a few tens of millions of years. Their analysis allows astronomers to decode orbital dynamics, measure the influence of tidal interactions, and observe mineral sublimation. For the uninitiated, it is essential to clearly present the context, mechanisms, and stakes of these discoveries to grasp the importance of what they reveal about the vulnerability of certain extrasolar worlds. First stop, the planet BD plus 4868 AB. This technical name designates a world subject to fascinating observation. Telescopes and spectrometry instruments reveal a trail similar to a comet's tail around this planet. Astronomers speak of a silicaceous cometary tail, a flow of mineral particles expelled from its surface or atmosphere. Silicates, rich in silicon and oxygen, make up a major part of the rocky crust of many terrestrial planets. This trail is not just a visual spectacle. It indicates that the planet is losing part of its matter under extreme conditions. To understand this escape, let's imagine BD plus 05, 4868 AB, very close to its star. The closer the planet is, the more energy it receives in the form of light and heat. At a certain distance, the temperature reaches hundreds, if not more than 1,000 degrees Celsius, beyond what rocks can withstand without melting or partially evaporating. At the same time, the gravity of the star and the planet's rapid rotation generate strong tidal forces. These stretching and compressing forces come from the combined attraction of the planet and the star, causing intense mechanical stress that gradually weakens the surface and interior of the globe. Researchers estimate that the erosion of BD plus 4868ab is rapid, about 1 Earth radius lost every 1 million years. This rate, although long for a human lifespan, is swift on a planetary evolution scale. This estimate relies on the observation of the silicaceous cometary tail, whose size, brightness, and composition are analyzed through advanced spectroscopy. The study of the light emitted or absorbed reveals the presence of silicon-rich rocks dispersed at extreme temperatures. On the scientific level, BD plus 4868ab illustrates rock sublimation. Sublimation corresponds to the direct transition from a solid state to a gaseous state. On Earth, dry ice is a familiar example. Here, rocks heated to very high temperatures release elements like sodium or silicon in the form of vapor. This cloud of particles is then carried into space by stellar radiation. The planet gradually loses part of its structure, creating a trail visible to instruments. Under these extreme conditions, orbital stability becomes illusory. As the planet loses mass, it can move even closer to its star until it disintegrates or contributes to a debris disk around the star. BD 4868ab offers a rare opportunity to observe this stage of disintegration, still little known. Now, let's move on to TOI 2431b, a striking example of a short-lived planet. Recently discovered, it completes a full revolution in just 0.22 days, or about 10 hours. By comparison, Mercury takes 88 days to make one orbit. This world spins at an extreme speed, subjected to an intense flow of heat and radiation. Its star is an M or K-type dwarf, smaller and less luminous than the Sun, but the proximity compensates for this weakness. The planet receives such powerful radiation that its surface easily exceeds 1,000 degrees Celsius. This heat accelerates erosion and sublimation. Light gases escape quickly, while denser layers can melt or outgas. The planet thus loses its envelope, leaving a core that becomes increasingly reduced. The fate of TOI 2431b is brief on a cosmic scale. It could disappear completely in about 30 million years, a gigantic interval for humans, but fleeting compared to the lifespan of its star, which can extend over billions of years. This process encompasses the loss of volatile elements, followed by the disintegration of the mineral structure, subjected to extreme temperatures and tidal forces, leading to dispersion in space or a fall onto the star. Tidal forces play a key role in this accelerated destruction. They result from the difference in gravitational attraction between the planet's near side and far side, causing deformations and internal heating. This heating maintains volcanism and seismic activity, which expel materials and promote mass loss. This vicious circle amplifies the disappearance of the world. For TOI 2431b, these phenomena increase the likelihood of a rapid end. Astronomers continue to observe the planet using space telescopes and ground-based instruments, measuring variations in its star's radial velocity to estimate the rate of mass loss. This data feeds celestial dynamics models, refining understanding of the limits of planetary migration before destruction. BD plus 4868, AB, and TOI 2431b are true natural laboratories. They offer a unique glimpse into extreme phenomena related to gravitational interactions and rock sublimation due to their proximity to a star. Researchers strive to determine their chemical composition to identify resistant minerals and the internal processes triggered by high pressures and temperatures. Studying the residual atmospheres, even very thin ones, provides insight into surface and internal geology using methods such as infrared spectroscopy and transit analysis. These planets also interest specialists in star system formation. While it was thought that planets were stable for billions of years after migration, the existence of BD plus 05 4868, AB, and TOI 2431b reveals dramatic trajectories where the planet plunges toward the star, exposed to extreme light intensity until its disintegration. The resulting debris could enrich the star's chemical composition or form dust rings destined for other bodies. Observation requires extreme precision. The detected radial velocities are sometimes minute, and the transit's rapid due to the brevity of the orbits. Space telescopes like TESS and high-resolution spectral ground-based instruments work in synergy to validate these signals. This data is essential for confirming the existence of a cometic tail and measuring the evaporation rate. These discoveries influence our vision of habitability. The quest for planets in the habitable zone remains current, but BD plus 05, 4868, AB, and TOI 2431b remind us that most exoplanets evolve outside this framework, exposed to extreme conditions. They illustrate the diversity of planetary destinies, reinforcing the understanding of the violent processes that shape the universe. At the heart of our cosmic journey, we now enter a distant region of the galaxy, located between 10,000 and 25,000 light-years from the Sun. In these vast stretches, the Milky Way presents a reinforcement of its stellar density called the galactic bulge. This sector has fascinated astronomers for a long time, as it concentrates a very large number of stars gathered towards the center of the galaxy. Today, thanks to a specific observation method called gravitational microlensing, several teams have detected new exotic worlds, some orbiting distant stars, others drifting without a sun to illuminate them. To grasp the essence of gravitational microlensing, one must return to a fundamental principle of general relativity. Every mass curves space-time around it. When the mass is significant, like that of a star or a stellar ensemble, this phenomenon bends the light that passes through this area. This bending acts like a lens, similar to a magnifying glass that enlarges an object placed behind it. In the cosmos, this lens is not made of glass, but constituted by the mass of a star closer to us. Thus, if a distant star in the galactic bulge catches our attention, and a second star, closer to Earth, passes exactly between our gaze and this source, the light from the source seems to intensify briefly before returning to its normal intensity. This temporary brightening manifests the gravitational microlensing. It is as if the nearby star focuses the light of the background star, creating a transient peak of brightness detected by our instruments. The gravitational microlensing does not only reveal the presence of the foreground star. If this star has planets, their gravitational field can cause slight anomalies in the observed light curve. This phenomenon thus allows the detection of exoplanets even without transits in front of their star or radial signature. This method reveals very distant planets, as it does not require the planet to emit or reflect much light, but simply to bend the rays from an observed star. Several observation programs have specialized in the detection of microlenses toward the galactic bulge. Among them are primarily the Korean and international collaborations KMT for Korea Microlensing Telescope Network, as well as the MOA project, Microlensing Observations in Astrophysics. Thanks to these efforts, astronomers constantly monitor tens of millions of stars in order to identify temporary variations in brightness. Each microlensing event is analyzed to determine if it hides the signature of one or more planets. For the year 2025, several identifications have been announced under codes such as KMT 2024 BLG 0404 LB, KMT 2024 BLG 1209 LB, MOA 2022 BLG 033 LB, KMT 2023 BLG 019 LB, and KMT 2023 BLG 1896 LB. These sequences appear complex, but they correspond to the date of detection, the observation area, and the indication of a planet. Detailed analysis of the light curve has revealed objects of sub-Saturn mass, thus less massive than Saturn, or of Jovian mass, meaning as massive or more than Jupiter. In the latter case, They are often referred to as giant gas planets, like Jupiter and Saturn in our solar system. According to several teams, these planets would be located on average at projective distances between 2 and 4 astronomical units from their host star. This distance corresponds to the apparent separation in the plane of the sky, although the three-dimensional position is sometimes more uncertain. These discoveries enrich the mapping of planetary distribution in the galaxy, including the central regions where the high density of stars favors the microlensing method, while other techniques like transit or radial velocity are difficult to apply. The continuous observation of the bulge aims to better understand the planetary structure in these ancient and populated zones of the Milky Way. Each new detection deepens our knowledge of the formation of planetary systems in environments different from that near the Sun. Beyond the orbiting planets, some objects discovered or observed through long-exposure imaging seem to float without being tied to a star. They are called orphan or rogue planets. These celestial bodies, without a guiding light, move through the interstellar void, each following its own trajectory, far from the stability of a classic stellar system. During deep imaging campaigns, 2 of them have been identified, O05's 41280 and O06. 089. These mysterious entities have masses estimated between 8 and 12 times that of Jupiter. To understand, let's recall that Jupiter, the most massive planet in the solar system, is already very imposing. Beyond several Jupiter masses, it becomes difficult to know whether it is a giant planet, a brown dwarf, or an object in between the 2 categories. Beyond this classification, the primary enigma concerning these free planets is their origin. How did they end up isolated in space, far from a nurturing star? 2 main hypotheses dominate. First, dynamic ejection within their original system, when a planet undergoes gravitational instability or comes too close to a massive companion. Secondly, brown dwarf-like fragmentation, a partial collapse of a gas and dust cloud that doesn't produce a star, but an isolated object of planetary or substellar mass. Some orphan planets probably began their existence around a young star before being expelled through violent gravitational interactions. Imagine a forming stellar system. Multiple protoplanets interact. Close orbital encounters, or the influence of a neighboring star, injects enough energy to catapult a planet out of the system. This planet then leaves the influence of its sun and drifts forever. The second hypothesis, that of brown dwarf-like fragmentation, suggests that a vast cloud of gas and dust collapses locally, forming small cores too light to trigger the nuclear fusion reactions necessary for star formation. If this concentration of matter nevertheless exceeds the usual planetary mass, it gives rise to a hybrid object, neither a star nor a classic planet. It is often referred to as a brown dwarf beyond a certain mass limit. Below this, the distinction becomes blurry. The object can be considered a very light brown dwarf or a supermassive planet. In any case, the discovery of these wandering planets generates a keen interest among exobiologists and astrophysicists. It raises the question of the potential habitability of bodies drifting alone in space. At first glance, favorable conditions for life seem impossible without a nearby source of light and heat. Yet some suggest that internal heating mechanisms may persist, for instance, through the natural radioactive decay of elements or residual heat accumulated during formation. In extreme situations, if the object is massive enough to retain a thick ice mantle, or if it possesses an internal moon, it is conceivable that layers of liquid water could survive shielded from the low external temperatures. This subject fuels many scientific discussions, although no evidence yet demonstrates that a life comparable to ours could exist on these solitary worlds. From a research perspective, the challenge is to catalog and study these isolated or distant planets to understand how the galaxy produces and redistributes planetary matter. Gravitational microlensing, intensively used by programs like KMT or MOA, offers a unique window on this phenomenon. When a solitary planet randomly aligns with a background star, it briefly acts as a detectable gravitational lens from Earth. The astrophysicist then observes a very brief, luminous amplification curve without the signature of an associated star. The detection of objects such as O005S41280 and O006S089 proves the feasibility of this method, even though it remains complex and requires nearly permanent coverage. A microlens event, especially for a low-mass isolated body, may last only a few hours, requiring an essential rapid instrumental response. This is why these discoveries are rare, but each new identification confirms the existence of a large number of orphan planets. Their masses, estimated to be between 8 and 12 times that of Jupiter, place them in an ambiguous category. Jupiter, the unit of Jovian mass, is itself much heavier than Saturn, which weighs about a third of its mass. Thus, 8 times Jupiter represents a substantial mass. Specialists often place the boundary between gas giants and brown dwarfs around 10 to 13 Jupiter masses, the threshold beyond which deuterium fusion can occur. This fusion is not equivalent to the hydrogen fusion that powers stars, but it indicates that the object can produce a bit of energy through fusion. The two detected bodies could therefore be very low mass, brown dwarfs capable of this phenomenon, or giant planets. Whatever their final classification, these wandering bodies illustrate the impressive diversity of planetary formation and evolution in the galaxy. The results obtained by microlensing enrich our understanding of the distribution of planets. Until now, discoveries mostly concerned nearby zones or bright stars, favoring transit or radial velocity methods. Today, we know that in the galactic core, Saturn-sized or Jupiter-sized planets in wide orbits or free-floating populate these regions. The events referenced as KMT 2024 BLG0404LB, KMT 2024 BLG 129LB, MOA 2022 BLG 033LB, KMT 2023 BLG 0119LB, and KMT 2023 BLG 1896LB illustrate the pace of discoveries. Each corresponds to a signal recorded during an observation campaign directed towards the bulge, with an international collaboration gathering telescopes on several continents, ensuring near-continuous monitoring. The parameters describing these planets, such as masses and orbital or projective distances, complement theoretical data to refine formation models. For example, questions arise regarding when giant planets form in a system. This question is particularly relevant in the bulge, where the environment is often turbulent, with potential stellar encounters and intense radiation. Moreover, the high metallicity of some ancient stars modifies the conditions of the protoplanetary disk, which can favor or complicate the birth of giants depending on the configuration. Furthermore, the conformation of sub-Saturn objects, thus slightly less massive than Saturn, sheds light on the continuum between heavy rocky worlds and gaseous planets. These objects could be planetary cores that began gas accretion without reaching the critical mass to become true giants. Such a population would contribute to the great diversity of profiles observed today, showing that planetary formation is a continuous and flexible process, influenced by initial temperature, disk density, chemical composition, and the presence of perturbing objects. The high stellar density towards the bulge can generate complex microlens configurations, where the source and lens star are difficult to distinguish in the images. Astronomers then use complementary methods, such as infrared observation or high-resolution imaging, to better visually separate the lens star from the background. Sometimes, measuring the displacement of the lens star over several years lifts the ambiguity regarding its distance and mass. Teams combine microlensing, astrometry, and direct imaging to obtain a more accurate picture of the system. Studying the global galactic dynamics, every new planet detected, whether in orbit or free-floating, constitutes a piece of the puzzle of stellar and planetary evolution. In the galactic center, old and young populations of stars coexist, offering astrophysicists a field to test formation models under different epochs and conditions. The presence of several massive planets in this region shows that, despite tidal forces, gravitational collisions, and variable metallicity, the birth of gaseous objects remains possible. Logistically, these recent microlens detections open avenues for improving the sensitivity of telescopes and the relevance of automatic algorithms. The KMT and MOA campaigns, responsible for the discoveries, benefit from wider sensors and real-time automated analyses. As soon as an unusual luminosity peak is detected, an alert is sent to the global scientific community. Telescopes across the globe can thus intervene without delay, preventing the loss of very short events. Narratively, one can imagine that upon crossing the 10,000 light-year barrier, our imaginary spaceship perceives the incandescent pupil of the galactic bulge. As it ventures further, it detects the fleeting glimmers of systems signaling their presence through variations in brightness. Like lighthouses in the night, microlensing events tell the story of invisible planets, revealed when their gravitational field interposes in front of the light of a distant star. Along this path, ghostly silhouettes of orphan worlds emerge, deprived of a sun, but pursuing their destiny in the cosmic vastness. In this quest, the discoveries of free planets like O005's 41280 or O006S0089 symbolize the frequent unpredictability in the universe. They evoke nocturnal runners on deserted roads without a fixed destination. Understanding why they drift and estimating their number in the galaxy remains one of the major challenges of modern astronomy. Some estimate that their population rivals or even surpasses that of orbiting planets, underscoring the phenomenon's magnitude. The story is just beginning. Future observations from Earth or with space telescopes will continue to explore the heart of the Milky Way. More ambitious missions are envisaged, aiming to scrutinize the inner part of the galaxy daily or refine parallaxes in astrometry. Space agencies and private consortia aim for an ever more complete inventory, not only to count rogue planets, but also to assess the distribution between giants, sub-Saturn, super-Earths, and smaller worlds. Each new publication enriches databases open to all. Passionate amateur astronomers compile this information and decipher light curves to reproduce microlensing analyses. As software evolves, some past events are rediscovered in archives, suggesting that many planets are still waiting to be revealed.